Okay, in my previous classes, so I was discussing the solutions for the questions in the assignment in collisions. I have already discussed the solutions for the questions numbering from 1 to 16 in the assignment in collisions. So next I am going to continue the discussion of the solutions of the remaining questions, starting from question number 17. Look at the question number 17 on the screen. I am going to discuss the solution for this question in a one-dimensional collision between two identical particles A and B. B is stationary and A has momentum P before impact. During impact, A gives impulse J to B. The coefficient of restitution between A and B is, so here A is the first body. Suppose it has initial velocity u1 before collision, and B is second body which is initial at rest before the collision. So during the collision, A gives impulse J to B. That means impulse J given to B by A will be directed to the right side in the figure. So initial momentum of A before collision, you can write mu1, which is given to P. Let v1 be the velocity of A just after collision and v2 be the velocity of B just after collision. So impulse given to A impulse given to B by A. J is impulse given to B by A. Of course, impulse given to A by B will also have same magnitude, but in opposite direction. So impulse given to B by A is towards right in the direction of the momentum P. So if you give positive sign for the initial velocity u1 and momentum of A before collision, can give positive sign for impulse given to B by A towards right, which is also in the same direction. So impulse given to A by B will be equal and opposite to the impulse given to B by A. So impulse given to B by A is equal to change in momentum of B. Change in momentum of B is equal to final momentum of B minus initial momentum of B. That is mv2 minus mu2. M is the mass which is same for both the bodies. Here second body is initial at rest, so u2 is 0 here. So you can write, if you substitute u2 equal to 0 here, you can write J equal to m into v2, or v2 can be written as J by m, and u1 can be written as P by m. Then here, in any coefficient of restitution between the two colliding bodies is given by v2 minus v1 by u1 minus u2. Here u2 is 0. You can write u1 equal to P by m, v2 equal to J by m. So you have to find v1 in terms of P, J and m. So for one dimensional collision, you can write m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. So here both the bodies have same mass. Mass of each body have denoted by m. So m1 equal to m. m2 is also equal to m. v2 you can write J. J by m, or m like this. m1 u1 is in each, m1 is equal to m. u1 is P by m, or directly can write m1 u1 equal to P. u2 is 0. So you get So you can cancel, you can solve for V1 here, MV1 equal to P minus J. Or V1 you can write P minus J by M. Substitute all these values in this equation and simplify it. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem and complete the calculation part also yourself. This problem was given one of the previous MSET examination, 2003. I think I remember it as 2003 MSET medical. So V2 is J by M. V1 is P minus J by M. U1 is P by M. And U2 is 0. So you can simplify that. You get 2J minus P by P. Can divide each term separately with denominator. So you can simplify that. You get 2J by P minus 1. In case you need more time to copy the solution, you can take a pause and copy the solution. So for question number 17, first option will be the answer. Then look at the next question here. Question number 18. The question has statement 1 and statement 2. Of the 4 choices given after the statement, choose the one that best describes the two statements. Statement 1. A point particle of mass small m moving with speed v collides with stationary point particle of mass m. The maximum energy loss is possibly given as small f equal half small m into v square. Then small f equals small m by capital M plus small m. Statement 2. Maximum energy loss occurs when the particles get stuck together as a result of collision. So in the theory part of one-dimensional inelastic collisions, I discussed that for given initial velocities of the two colliding bodies and for given values of the masses, maximum possible loss of kinetic energy takes place when the two colliding bodies stick together or move together after collision. Such collisions are said to be completely inelastic. So statement 2 is definitely true, but we have to check up the statement 1. Let us check up do the calculation related to the statement 1 here. So here's the first particle which has mass small m is moving with speed v before collision. Second particle is initial at rest. So initial moment of second particle is 0. So momentum just before collision means it can be taken as momentum of the first particle of mass small m, which is equal to small m into v. That can be written as momentum just after collision. Momentum just after collision, you can write capital M plus small m into v1. Here v1 is the magnetic velocity just after collision. So to find the ratio of the final to initial kinetic energies after and before collision, you have to find the ratio of the final and initial speeds after collision and before collision. So v1 by v, you can write small m by capital M plus small m. So the ratio of the final kinetic energy after collision to the initial kinetic energy before collision. I write it as kf by ki. Ki represents the initial kinetic energy just before collision. That is equal to initial kinetic energy of the first particle of mass small m, which is equal to half small m into v square. Kf is the final kinetic energy of the combined mass of system of the two particles just after collision. That you can write half capital M plus small m into v1 square. This problem is similar to the calculation we have discussed in ballistic pendulum, similar to that. So capital M plus small m by small m into v1 by v whole square. We can substitute v1 by v equal to small m by capital M plus small m. Two sources. So we'll substitute the value of V1 by V equals small m by capital M plus small m from this equation into this equation. So you get Kf by Ki, capital M plus small m by small m into small m by capital M plus small m whole square. So ratio of the final kinetic energy to the initial kinetic energy. That is the kinetic energy just after collision to the kinetic energy before collision. Kf by Ki is equal to small m by capital M plus small m. So the ratio small m by capital M plus small m represents the ratio of the final kinetic energy just after collision and the initial kinetic energy just before collision. But kinetic energy loss of small f into half mv square. So definitely statement 1 is not correct. But still I would like to calculate the true value of small f here. Not only just finding whether statement 1 is true or not. So fractional decrease, yes, small f represents fraction of the initial kinetic energy which is lost during the collision. Here small letter f represents the fraction of the initial kinetic energy of the first particle which is lost due to the collision. Or we call it as fractional decrease in the kinetic energy. So fractional decrease in the kinetic energy due to the collision is equal to actual decrease in the kinetic energy during the collision divided by initial kinetic energy. So actual decrease in the kinetic energy during collision is equal to Ki minus Kf divided by initial kinetic energy. Gives you the fractional decrease in the kinetic energy. This you can write Ki by Ki minus Kf by Ki. You can substitute Kf by Ki equal to small m by capital M plus small m. So this is 1 minus small m by capital M plus small m. If you want to copy the solution of this question, you can take a pause and copy this solution. You can simplify this further. So you get small f equal to, finally you get small f equal to capital M by capital M plus small m. But here statement 1 you are given that small f has small m by capital M plus small m. So greatest, the fraction of the maximum possible fraction of the initial kinetic energy that can be lost during the collision is capital M by capital M plus small m. So the statement 1 is not correct, but statement 2 is correct. So look at the options here that is given here. Statement 1 is false, statement 2 is true. That means first statement will be the answer. Next, first option is answer. See the next question. Question number 19. Bullet of mass 50 gram moving horizontally strikes a wooden block of mass 950 gram, which is initially at rest on a rough horizontal floor. Nu equal to 0.25. Gets embedded into the block. After the collision, the combined mass travels 5 meters along the floor. What was the initial speed of the bullet? You have to take g at 10 meters per second square. So to answer the question, you have to apply the work energy theorem for motion after collision, or you can use one of the results discussed in friction for motion after the collision. First, applying the conservation momentum principle, that is momentum just after collision, equal to momentum just before collision. Let small m denote the mass of the, or you can write for any one dimensional collision, you can write m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Here the bullet and the block move together with the common velocity after collision. So let V1 be the velocity of the combined mass just after collision. So you can find U1 if you know V1. U2 is 0 here. So initial velocity is second particle is 0. So therefore to find U1, we have to first find V1. So initial speed of the bullet before collision is equal to M1 plus M2 into V1 by M1. You can also substitute the values. M1 is 50 grams, M2 is 950 grams. So M1 plus M50 plus 950, that is 1000 grams or 1 kg. So if you substitute here, otherwise, the masses, this is 1 kg by 50 grams means 50 into 10 power minus 3 kg into V1. So you get U1 equal to 20 times V1. So we can apply the work energy theorem for motion after collision. The total mass after collision can be denoted by M, which is equal to M1 kg, that is M1 plus M2. The combined mass starts moving with velocity V1 after collision and travels some distance S along the floor before it comes to rest, before its velocity becomes 0. According to the work energy theorem, for motion after collision, the change in the kinetic energy of the combined mass for motion after collision is equal to total work done by all the forces acting on the combined mass during motion after collision. That is work done by the frictional force plus work done by the gravitational force plus work done by the normal reaction. Final velocity of the combined mass for motion after collision along the floor, we can take it as 0. Final kinetic as 0. So final kinetic energy, you can take it as 0. Initial kinetic energy combined mass for motion after collision half mv1 square. Work done by the force of friction will be, force of friction acts opposite displacement. So work done by the frictional force will be Fs cos 180. Because force of friction acts opposite direction of displacement. So angle between direction of the friction and direction of the displacement for motion after collision is 180 degrees. Work done by gravitational force is 0 because gravitational force acts in the vertical direction. Displacement is in the horizontal direction. That means work done by the gravitational force will be 0 because the gravitational force acts perpendicular to displacement. The same way work done by normal reaction is also 0. That means for motion after collision, 3 forces act on the combined mass. Its weight mg, that is the gravitational force, and normal reaction force of friction. So magnet of friction for along acting on the combined mass during motion after collision, you can write product of coefficient of friction into magnet of normal reaction. So magnet of the normal reaction can be taken as equal to the magnet of the weight mg of the block. So magnet of friction, you can write nu mg. Therefore, you can write same result. You can as well use this result directly. If you remember, one of the results I discussed in one of the special cases in the friction chapter. As I told you, if a block starts moving with some initial velocity u along a rough horizontal floor, then the distance with the block travels along the rough horizontal floor before it stops during retarded motion under the action of 3 forces, weight mg, normal reaction, friction, given by u square by 2 nu g. Here for motion after collision, v1 is the initial velocity. So if you remember that particular conclusion which we discussed under the small heading stopping distance, You can directly write this step after this step. Okay, now V1 you can write root of 2 nu G into S. You can write nu equal to 0.25 and G equal to 10 meter per second square and S is 5 meters. You can simplify this. You get V1 equal to 5 meter per second. You can substitute this value of V1 from second equation into the first equation. If you want to copy the solution, you can take a pause and copy the solution of the problem. I'm coming back to the first equation. If you substitute value of V1 from second equation into the first, you get U1 equal to 20 into 5 meter per second or 100 meter per second. That's the answer. This problem I have set myself originally. In case you need more time to copy the solution of the problem, you can take a pause and copy the solution of the problem. For question number 19, which I just now discussed, the first option will be the answer. See the question number 20. A ball falls vertically onto a floor with momentum P and then bounces repeatedly. The coefficient of restitution is E. The total momentum imparted by the ball to the floor is. They are given 4 options in terms of P and E. This question I have discussed already in one separate class. I have taken one separate class or for one special case. I have discussed one special case in one of the previous classes in collisions, where ball is dropped from certain height onto a horizontal floor. And I have discussed, given you the list of the conclusions and along with explanations. And that is the last conclusion I have given. The total imparted by the ball to the floor during all collisions before it finally stops, or total impulse imparted to the floor by the ball during all collisions with the floor is given by P into 1 plus E by 1 minus E. So I already discussed this case in detail, so I don't want again discuss that. So fourth option will be the answer for this question. See the question number 21. Ball 1 collides head-on with another identical ball to at rest on a horizontal surface. For what value of coefficient of restitution E? The velocity of second ball becomes 3 by 2 times that of first ball 1 after collision. So here both the balls are identical, means both the balls have same mass m. So mass of second ball is same as the mass of the first ball. Let m denote the mass of each ball. And the second ball is initial at rest. U2 is 0. And after collision, you have to find the value of coefficient of restitution so that velocity of second ball after collision becomes 3 by 2 times that of the first ball. So V2 can be taken as 3 by 2 times V1. So we can write M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2 for any one-dimensional collision. Here both the balls have same mass denoted by M. So you can write V2 equal to 3 by 2 times V1. And second ball is at rest, so U2 is 0. So this you can simplify it further. So you get 5 by 2 times V1 equal to U1. So the coefficient of restitution E is given by V2 minus V1 by U1 minus U2. You can substitute V2 equal to 3 by 2 times V1. in the numerator. The denominator can substitute u1 equal to 5/2 times v1. u2 is 0. So this can simplify it further. So v1 by 2 divided by 5/2 v1. So we get e equal to 1/5. That's the answer. In case you need some time to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 21, which I have just now discussed, first option is answer. See the question number 22. A particle of mass m1 moves with speed v and collides head-on with a stationary particle of mass m2. The first particle continues to move in the same direction. If m1 by m2 is, so the first particle will continue to move in the same direction if v1 and u1 have same sign. That means if u1 initial velocity, u1 means initial velocity of m1 before collision, if it is given positive sign. If you give positive sign for v1 also in the calculations, that means after collision first particle will continue to move in the same direction. If you remember one of the results I have written in the past, you can answer the question very fast. So in a one-dimensional collision, if the initial velocity second particle is 0, then v1 can be written as m1 minus em2 by m1 plus m2 into u1. So m1 continues to move in the same direction if m1 minus em2 is positive. If u1 is positive and v1 also comes out to positive after calculation, it means that first mass m1 continues to move in its original direction. In some of the problems, u1, if you give positive sign for u1, v1 may be negative. In that case, it means that first mass m1 moves back opposite to its original direction of the motion after collision. So if you give positive sign for u1 and the first particle continues to move in the same direction, v1 is also positive. That means m1 minus em2 must be positive. m1 minus em2 will be positive if em2 is less than m1. That means m1 continues to move in the same direction after the collision if m1 minus em2 is positive, or m1 minus em2 is greater than 0, or m1 is greater than em2, or you can say em2 is less than m1, or E is less than m1 by m2. That's the answer. But I would like to discuss alternate method for this question, because you may not remember this conclusion which I discussed in the past. So therefore, I would like to discuss the alternate method for this question. In case you want to copy the solution, you can take a pause and copy the solution. So now I am discussing the alternate method for the same question. So any problem in one-dimensional collisions can be solved by using the two equations. M1 V1 plus M2 V2 is equal to M1 U1 plus M2 U2. That is one equation, and E equal to V2 minus V1 by U1 minus U2. So using the first equation, M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2. Here second particle is initially at rest, so U2 can be taken as 0. So second term on the right side of the equation will vanish. So in any one-dimensional collision, you can write E equal to V2 minus V1 by U1 minus U2. So here U2 is 0, or V2 minus V1 E times U1 minus U2. So we can eliminate V2 from the two equations so that we can find V1 in terms of U1. So V2 can be written as V1 plus EU1. I have taken U2 to be 0 here. So we can substitute the value of V2 from second equation into the first equation. So M1 V1 plus M2 into V1 plus EU1 equal to M1 U1. Can solve this equation for V1. V1 into M1 plus M2 equal to M1 minus EM2 into U1. That means I am just deriving the same result which I have directly used in the previous method. So the first particle of mass M1 continues to move in the same direction after collision. If V1 and U1 have same sign, if you give positive sign for initial velocity U1 before collision, then M1 continues to move in the same direction after collision. V1 is also positive. That means M1 minus EM2 must be positive, or EM2 must be less than M1. So M1 moves in same direction after collision with M2. That means M1 continues to move in its original direction after collision if E is less than M1 by M2. If you want to copy this calculation, you can take a pause and copy the calculation. So here, for this we have already arrived at the conclusion that EM2 should be less than M1, or E should be less than M1 by M2, or you can say M1 by M2 must be greater than E. That means second option is the answer for question number 22. Look at the question number 23. Bullet of mass 50 gram moving with velocity 500 meters per second passes through a wooden block of mass 1 kg. The block is resting on a smooth horizontal floor. After passing through the block, the velocity of the bullet is 200 meters per second. Its velocity relative to the block is. So for one-dimensional collision, we can first write M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2. M1 is the mass of the bullet, which is given to 50 grams. M2 is the mass of block, that is 1 kg. So here block is initial at rest. So you can substitute all the given values. M1 is equal to 50 grams or 50 by 1000 kg. And after the collision, the bullet comes out of the block with a velocity of 200 meters per second. So V1 is the velocity of M1 just after collision. That means velocity of the bullet after collision. That is 200 meters per second. M2 is the mass of the block, that is 1 kg. V2 is the velocity of the block just after collision, which you have to first calculate. M1 is 50 grams or 50 by 1000 kg. U1 is the initial velocity of the bullet before collision, which is given to be 500 meters per second. The block is initially at rest, so initial velocity of the block before collision is 0, or U2 is 0. This equation you can simplify to find V2. So velocity of the block just after collision, you get 15 meters per second if you simplify this. That means after the collision, the block is moving with the velocity V2, and the bullet with mass M1 is moving with velocity V1 in the same direction. Because both the velocities are in same direction, when the two velocities are in the same direction, magnitude of relative velocity of one body with respect to another body will be equal to difference in the magnitudes of the velocity of two bodies. That means velocity of bullet relative to block after collision. Can write it as V1 minus V2 because both the velocities are in the same direction. And V1 is here 200 meters per second. V2 is 15 meters per second. So you get the answer as 185 meters per second. If you want to copy the solution, you can take a pause and copy the solution of the problem. So for question number 23, second option is answer. See the question number 24. A moving solid ball makes head-on collision with a stationary ball. After collision, first ball comes to rest. 50% of kinetic energy lost in the collision. The question of restitution between the balls is. So second ball is initial at rest, so initial after second ball is 0. So you are not given the initial velocity of the first ball before collision. And you are not given the ratio of the mass of the two balls. Therefore, we are not going to use the equation direct formula which are given for kinetic energy lost in one dimensional collision. Half M1 M2 by M1 plus M2 into U1 minus U2 whole square and 1 minus E square. That equation I am not going to use now because you are not given the ratio of the masses or the individual masses. You are not given the initial velocity of the ball. So first it is given that after collision, first ball comes to rest. So V1 is 0. Before collision, second ball is at rest. So U2 is 0. So applying first conservative amount of equation M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2. This is the equation which you can write for all one-dimensional collisions. So here V1 is 0, therefore first term on the left side becomes 0. U2 is 0, therefore second term on the right side. First term on the left side becomes 0 and second term on the right side. So you get M2 V2 equal to M1 U1. Call it as question number 1. So here it is given that the final kinetic energy of system of the two bodies after collision can be taken as 50% of initial kinetic energy. because 50% of the initial kinetic energy is lost during the collision. When 50% of initial kinetic energy is lost during the collision, the final kinetic energy after collision will be 50% of the initial kinetic energy before collision. So final kinetic energy after collision, you can write 50 by 100 times the initial kinetic energy before collision. So the final kinetic energy after collision is equal to final kinetic energy of second mass m2 after collision. Because the first mass m1 comes to rest after collision. That means final kinetic energy of the mass m1 after collision is 0. So total final kinetic energy of the two bodies after collision means final kinetic energy of m2. It's equal to 50 by 100 times the initial kinetic energy before collision. Second mass m2 was initial at rest. So initial kinetic energy second mass m2 was 0. Therefore total initial kinetic energy before the collision is equal to initial kinetic energy of m1 before collision. So you get m2v2 square is equal to half of m1 u1 square. This is called equation 2. 50 by 100 becomes 1 by 2. Now we will divide the equation 2 with equation, because to find quotient of restitution, you must know the ratio of, we must know v1 and v2 in terms of u1. So from first and second equations, if you divide the second equation with the first, m2v2 square divided by m2v2 is equal to half m1 u1 square divided by m1 u1. So you get v2 equal to half of u1. Therefore quotient of restitution, we can write E equal to v2 minus v1 by u1 minus u2. You can write v2 equal to half of u1. Given that v1 is 0, it's also given that u2 is 0. So you get quotient of restitution between the two balls is 1 by 2. That's the answer. In case if you want to find the ratio of the mass of the two balls, also you can find. Of course, that's not asked. For the given problem, 1 by 2 is the answer. But in case you are asked to find the ratio of the mass of two balls, that can also be found by substituting v2 equal to half of u1 in the first equation. So substitute v2 equal to half of u1 in the first equation. You get m1 by m2 is equal to 1 by 2, or m2 is 2 times m1. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for the question number 24, second option is the answer, which I have just now discussed. So in my next class, I am going to complete the discussion of the remaining 6 questions, numbering from 25 to 30 in the assignment in collisions.